Hey, what's up, guys? Today I want to talk about this another theorem in a complex analysis, and I think it's also very important, called the maximum modulus theorem. Okay, and if you want to see more complex analysis video, you can check below. Okay, hope you guys subscribe to my channel. Okay, so the idea is that let me just talk about the theorem. So the idea is that you take some complex, you take some subset and a complex plane, and this G required to be connected and open. So I hope you guys know what open is, open set, and the connected is connected set. And you have a G where maybe C is holomorphic. So holomorphic function is like the basic ingredient in the complex analysis, right? So if there is A belongs to G, such that f of A is a maximum, basically f of A greater than f of Z, for all Z belongs to G, then f is constant. Okay, so what it means is that suppose this is your G, and G is open, right? So G is open. If there is A where inside G, right? So G is open, right? So there's A is here. If f of A is greater than all the Z or the region, which is is greater or equal to f of Z for all the Z belongs to G, then f is constant. So basically, if f is a maximum inside inside the G, oh sorry, what's going on? What's going on? Oh, this is very nice. You can. Okay, so if A belongs to G, if f of A is maximum, then the f of f is constant is in G. Okay, so simply speaking is that maximum. So simply speaking is that if S is non-constant, means that the maximum appear on boundary cannot exist in the interior point, must appear on the boundary. Okay, so let's go through a proof. Okay, so proof is very simple, right? Because the idea is this is why I choose is open, right? So because now let's say this is G, A, this is A, right? And since A is open, so G is open set, so A is a interior point. So there is a delta, a small radius delta. So there is the delta greater than 0, such that this disk, let's say open disk, D delta A, so it's the center at A with radius delta, such that all this D delta A will inside the G. Okay, so now you can use the Cauchy theorem, right? Cauchy theorem tell you that f of A is 1 over 2 pi I. You do this D, let's say you choose gamma, which is a circle, right? So you gamma is a radius delta along this circle, and the f of Z minus A dz. Okay. Okay, so now here comes the idea. Here comes the point, right? So now you can make a change of variable. So you can because I choose circle, right? So I can let Z equals to A plus delta I theta. So I get f of A is 1 over 2 pi I, 0 to 2 pi. So f of A plus delta is equal I theta. So dz, say dz will be I delta is equal I theta d theta. So I get I delta is equal to I theta d theta. So I canceled. Okay, so I get a famous result. Basically, f of A is the average. So this is average, just average of the 0 to pi f of A plus delta I theta d theta. So this tell you that this f of A, this point f of A is if the it's a integral, right? You have a f which is integral along this circle. So f of A is the average of, you can view this as average, right? So it's the average on this circle. Okay, so now you know the trick, right? So it's obviously that this is obviously that if your f of A is maximum, then your intuition will tell you that all this f of A plus delta exponential I theta should be the same as f of A. So this is the intuition. But let me just provide a detailed proof. So you just take the absolute value. So you take the absolute value. Okay. So suppose this will give you what? This will give you less or equal to 0 to 2 pi fa plus delta I theta d theta. Okay. But this guy is less or equal to f of a by construction. But this is f of a. Okay. So by a continuity of f, the continuity f means that if there's a point here, let's say there's a point b here, such that f of b is strictly less than f of a, then by the continuity, there will be very small region such that at that region, f of b less than f of a. Then all the integral you get will violate this inequality. So the results must be all the points. So all the points on the circle must have the same modulus. So f of a plus delta exponential I theta must be the same as f of a for all theta. Okay, so now we only proved that there's absolute value is the same, but we didn't get our results, right? Because our results, so our goal is to prove that f of a plus delta I theta equals to f of a for every theta. But now we only have their modulus is the same. We only get their norm is the same. Okay. Okay, so now it's very simple. We take so what do we do? We just try to prove that if there is a phase difference, then the results will be different, right? So let's take f of a to be exponential minus alpha f of a. So alpha is just the phase. Okay, so one can say that alpha is the argument of f of a. Okay, then we just do exponential negative I alpha and do the integration. So we get 0 to 1 over 2 pi. We know that f of a is f plus a plus r, also delta I theta d theta. Okay. Okay, now we take the okay, so now we have this. Okay, so now let's take the real part. We take the real part of both sides. So for this part, I take real part. So real of absolute value still f of a. And this part, I can take the real part, right? So I get I want to get 1 divided by 2 pi, 0 to 2 pi. The real parts of exponential negative alpha f of a plus delta I theta d theta. Okay, let me just write down. So the real part of exponential negative alpha f of a plus delta I theta is less than or equal to the norm, right? Because it's only real part. So it's less or equal to the norm of f of a plus delta I theta, and less or equal to f of a by construction. Okay, so this term is less or equal to 0 to 2 pi f of a d theta 1 over 2 pi f of a. Okay, so that means that this part, by the previous argument, this part must be equals to f of the norm of the f of a. Okay, so what we get is that the real parts of exponential negative alpha f of a plus delta I theta must be absolute value of f of a. And then we also proved that we also showed that this is the same as this. So you combine these two, obviously that you get the f of a plus delta I theta is the same of f of a for every theta. Okay, so this is a proof. Okay, so we proved that all the points is the same on this radius. But per proof, go to here, you can choose this delta to be arbitrarily small, right? So all these region will be the same, and then you can extend it because it's real, right? So you can extend it, and finally all the G will have the same constant. Okay, so this is the proof. Okay, I think this is so let me just write down another version which is almost the same. So the absolute value value of a non-constant holomorphic function, on a connected open set, G cannot have local minimum, cannot have local maximum. You can also show that if you reverse all the sign, you get a same, right? So you can have local maximum or minimum points in G. Okay, so the proof is similar. It's just the same thing as previous what we did. We just a restatement. Okay, once you have this powerful, that you can also you can use this to prove so-called Schwarz lemma, which is another powerful theorem. But I think this is already very amazing. Okay, so see you guys next videos.